Hey guys, how are you? It is May 4th, and to use that bad expression, May the 4th be with you. Hopefully you're still with me. Acids and bases today, and our objective is to be able to calculate the pH of a solution. So how is this done? As we talk about acids and bases, very quickly, very early on, we wanted to be able to talk about pH. Now, the pH scale here is something that you've heard of before. Um, right in 7 here is neutral, which means same amount of acid as there is base. The word alkaline here will often be used to describe a base or alkaline solution. And the pH scale, which runs from 0 on this end all the way up to 14 at the most alkaline end. So here is the pH scale. And I've given you some examples on this pretty cool picture and that of what goes on here. What the pH scale is, and by the way, P stands, roughly it stands for power of hydrogen. How much hydrogen is in the solution. And it is a measurement. Now, what pH is, it is the negative logarithm of the hydrogen ion concentration. What? Yes, the negative logarithm of the hydrogen ion concentration. So that's what pH is, and this is how it is derived. So the more concentrated the acid, the lower the pH. And here's the formula up here for pH. It is the negative log of the hydrogen ion concentration. So you want to have this formula written down, and at your beck and call there, because you're going to need it. So what would be the pH of a 1 molarity hydrochloric acid solution? Well, the pH of this would be equal to the negative log of the molarity, which is 1. So the negative log, and I'm going to use square brackets here, of 1.0 molarity. Ran out of room. Okay. The negative log of 1 is 0. So the pH of 1 molarity hydrochloric acid is equal to 0. And that is how this works. So what is the pH of 0.1 molarity hydrochloric acid? Well, pH would be equal to the negative log of 0.01 molarity. So on your calculator, the negative key, the negative function, the log key, and then decimal 0.1, and you should get an answer of pH equal to 2. And again, on your calculator, the first key you hit is negative, then you hit log, and then you put in whatever value, in this case 0.01, and that should get you to the value of 2. So that is how we calculate pH. It's the negative log of the hydrogen ion concentration. So it lets us express these very small concentrations sometimes as whole numbers, and it makes it a whole lot easier to use. And that's the whole point of the pH scale, is to make pH, to make acidity something very easy to express. Now, this is going forward. I'm going to show you how you go backwards, and this would be finding the hydrogen ion concentration from the pH. So this would be my hydrogen ion molarity. And I'm finding this from the pH. So if the pH was equal to, say, 4.5, what would be the hydrogen ion molarity? What would be the concentration of the hydrogen ions? Well, in order to do this, we would go backwards, and we would want the antilog of the negative pH. So inverse key, log, and then negative pH. So 10 to the negative 4.5, like this. That's how I would put it into my calculator, and I would get an answer of 3.16 times 10 to the negative 5. So what that means is that my hydrogen ion molarity is equal to 3.6 times 10 to the negative 5, or 0.000316 molarity of the hydrogen ion, like that. And again, by using pH, we can take really small concentrations like that and express them as whole numbers. So rather than using a ridiculous small concentration like this, we simply express it as a pH of 4.5. All right, that's how it goes. I would practice that, by the way, on your calculator. We're going to do a little practice in a minute. What if it's a base? If it's a base, you actually have what is called POH. And the OH now stands for the power of the hydroxide. How much hydroxide is in the solution? It's how alkaline, or the alkalinity of the solution. And here's our formula again. POH is the negative log of the hydroxide concentration. So what is the POH of a 0.15 molarity sodium hydroxide solution? POH is equal to the negative log of the hydroxide. So POH is equal to the negative log of 0.15. And I'm going to use square brackets for molarity again. And I'm going to have to actually do this real quick on my calculator. Negative log 0.15. And I get 0.823 as my pH. I'm going to go with 0.82 as my POH. I think I said pH just a second ago. So my POH is 0.82. And that I'm okay with that. And that, again, you want to practice that and make sure that we are good with it. All right. So that's how we do POH. And again, we can go backwards and find the hydroxide from the POH. So say something like bleach or something. Say we have a POH equal to 3.2. And we want to know what is our hydroxide ion concentration, will be equal to X. So the hydroxide ion concentration would be equal to the inverse log, again, of the negative POH. So it would be equal to negative 3.2, and that would give us our hydroxide ion concentration. And again, I'm going to have to do this real fast. So I'm going to hit second log negative 3.2, and I get 6.3 times 10 to the negative 4. And that is the concentration of the hydroxide. If the POH is in the 3, the POHs will generally be in the negative 4. That's how logarithms work. Okay, that's how you go backwards. Third piece is this. pH, which is the power of the hydrogen, plus POH, which is the power of the hydroxide, is equal to 14. In other words, they both must add up to 14. So if the pH is 7, the POH added to it will equal 14, and therefore it would have to be 7 itself. If the pH was equal, say we had a pH equal to 6, then the POH would have to be equal to 8, because they would have to add up together to 14, like that. So it's kind of cool. If you know pH, then you pretty much know what POH is just by subtracting it from 14. It works very, very easily like that. All right, let's do a little manipulation with this and give it a try. So here are some examples, and I'm going to go through them and at the order that I think is the easiest for you. So if the pH is 2.56, then the POH has to be 11.44. Why? Because these two numbers have to add up to 14. pH and POH have to add up to 14. Now from the pH, I can come backwards here and find the hydrogen ion concentration, because that will be 10 to the negative pH, the inverse log of negative pH. And if we do that, we get 2.7 times 10 to the negative 3. Now the POH, I'm going to take that backwards and find the hydroxide ion concentration from that. And that again will be the anti-log of the negative POH. And from that, I would get 3.6 times 10 to the negative 12. Okay. So let's see how this works. Let's give this another try here. Let me find my markers. I'm just going to change color. now that I have the hydrogen ion concentration, I can go backwards and figure out what the pH of this is most easily. So it's negative log of the hydrogen concentration. And if I do that, I get 6.25 because I've gone negative log of the hydrogen ion concentration. Knowing that this now is 6.25, I know that this has to be 7.75 because, again, these two must add up to 14, pH and POH. And then I can go backwards from here now and figure out what the hydroxide ion concentration is. And I'd already calculated that out as 1.77 times 10 to the negative 8. By the way, if you multiply hydrogen ion and hydroxide concentration together, they're going to be somewhere around 1 times 10 to the negative 4. Don't do that. 1 times, happy handwriting, 1 times 10 to the negative 14. Stop it. Okay. Now, let's go and do the third line along here and see what happens with that one. So here I'm given the hydroxide concentration. So the easiest thing to do is to go back from this and find out what the POH is. I can't find any of the hydrogens right away because I'm given hydroxides. So I did that and I came out with a POH of 4.55. That I then used to determine that the pH here was 9.45. And then I went backwards from this to figure out what the hydrogen ion concentration was, and I came out with 3.55 times 10 to the negative 10. Okay. And then lastly, with a POH of 1.2, the easiest thing was just to find out that the pH there must have been 12.8. Then to use this value here was the first thing I did and come back, and this is 1.58 times 10 to the minus 13. And again, what we're doing is just using this up here. And then we did the same, or I did the same for this, and I got 6.3 times 10 to the negative second as that value. All right, this here would be an acid because of its low pH. This would also be an acid. Anything with a pH below 7 is going to be an acid. This would be a base because our pH is higher than 7, and this also would be a base with a pH of 12. So when we're doing acid or base, we always want to come off this first line or the pH value. So when you're doing these for homework, and I'm just hunting around trying to change color again, when you're doing this for homework, purple, 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 always come off of the pH to determine whether it's an acid or base, and don't change the screen on yourself. Wow, does that ever look like a hot mess? You might want to go through this. You definitely want to practice it, and that it is kind of basically a calculator trick, but you are just using logarithms both backwards and forwards to turn concentration into pH. That's what the pH scale is. It's an effective and easier way of using the hydrogen ion concentration to discuss acidity, and it's why we use it, because it is easy to use, even though at first glance here, it's not going to be that easy. All right. Have at it. I've given you some practice to do. I think the practice is fairly straightforward, and that is Monday's assignment. And we'll see where we are with this. We may want to practice it for some days before we're comfortable with it. I hope you had a fantastic weekend, and because it was gorgeous weather out there, and I hope you are ready to do this week. And I hope you found your calculator because you're going to need it. Be good. Take care. Bye-bye.